Can everybody hear me okay? All right. I don't know why you're in here when there's a pinball competition going on, but I do appreciate it anyway. So what we're going to be talking about is basically, skip the slide already, anti-reverse engineering by using debug symbols basically against their intended purpose. So normally, just to level set things a little bit, like when you think of like malicious symbols, maybe you think of like, oh, I'm going to name a function do thing X when in reality it does thing Y. But we're going to talk more about fooling the tools than fooling the analyst. And so I guess we'll get into it a little bit. So essentially what the topics today are going to be, we're going to talk about, so what are ELF symbols exactly? And then we're going to do some work on using fake symbols to break static analysis, analysis tools, using crafted dwarf debug information to hinder dynamic analysis, debugging, things like that. And then since most of this relies on the existence of debug symbols, we're going to do some work to basically detect and react to binary stripping dynamically. So first off, I just want to talk about what tools I've been testing against. So what we're talking about here is going to be like IDAPRO and Hexray's decompiler, Ghidra and its decompiler, Radare2, which I'm just going to call R2 because I can't roll my R's, which doesn't have a decompiler of its own, so we're mostly just talking about its static analysis capabilities. And then when we start talking about debugging and dynamic analysis, we'll throw GDB in as well. So just to get into this, I do want to level set things a little bit and say that we're not really talking about like vulnerabilities in these tools. It's not like buffer overflows in IDA or anything like that. We're just sort of exploiting trust assumptions and how these tools work and how that their analysis is actually implemented. So with that in mind, let's talk a little bit about how static analysis tools work. A lot of this may not be new to you. Bear with me as we, go through the basics. But so what static analysis tools do is they basically attempt to analyze how a binary works without actually running it. So just sort of loading it internally and seeing what can be inferred without actually executing it. So this is a pretty difficult job. So there's a lot that goes into this. Maybe the most important thing is just disassembling code in an equivalent way to how the processor is going to execute it. This is particularly difficult if you're talking about an architecture like x86, where instructions can be variable length. They don't have like really strict alignment requirements or things like that. So it's very important for the analysis tool to make sure that it's sort of starting and ending at the same point that the processor is gonna parse that binary. Another very important thing is just determining where functions begin and end, not just sort of a dumb disassembler that's going to go through every instruction, but actually being able to tell this is the start of a procedure and this is where that procedure ends. And then ideally being able to tell the types of variables that could be like function arguments, it could be return values, it could be local variables within within a procedure. And because these are pretty significant tasks, analysis tools do pretty much use whatever hints they can come by, and the biggest metadata source that they have when available is the debug symbols. So let's talk a little bit, So before we get into that, I do want to talk just a little bit about how decompilers work. So I think the term decompiler is a little bit of a misnomer because it kind of implies that it's working by reversing the steps that the compiler takes. It's really not. I would say a compiler in its simplest form is just, a decompiler in its simplest form is just a compiler with the input and output reversed. So this is an oversimplification, but if you were to imagine GCC is just a compiler where C is the input, assembly is the output. Hexrays is just a compiler where assembly is the input, C is the output. So that may seem like a distinction without a difference, but I think when we get into sort of the way decompilers work, it makes things a little bit more clear when you think of it as a compiler going through the same sort of steps that a compiler would take, just with a different end goal. So with that in mind, let's talk a little bit about symbols. I'm sure you already probably know a fair amount about this. Again, we're just level setting things, but symbols are basically metadata that's added to an executable to aid in debugging. So this could be function names, it could be function types, where those functions are located. It could be a map of source code lines to assembly lines, something like that. And with a couple of exceptions, for the most part, symbols are not actually required by an executable. They're there for the human operator who's reading a crash dump or using a debugger or something like that. And so the process of removing unnecessary symbols is referred to as stripping a binary. And so there's sort of a hierarchy of symbols that can come along with a binary. In general, you can categorize binaries by 3 levels of symbols. There's stripped binaries. They have no unnecessary symbol information. There's nothing there given to you because that's not actually necessary for it to run. And then there's basic symbols, which are usually implemented through a section called the symtab. We'll talk about that in a few, but that contains basic information about functions, nothing too deep. And then there's debug symbols. This is sort of the jackpot of reverse engineering, where this gives you just about as much information as you could ask for. And this is usually implemented as what's called dwarf data. And we'll get into specifically what that talks about, or what that contains. But generally, ELF files, unless you're doing something special with them, will default to that middle value, those basic symbols. So let's talk about what the symtab is. So the symtab is a section of a binary that's optional, since all symbols essentially are, that contains, as the name suggests, a table of symbols. And this table, well, it can contain a number of things, but really the one you usually care about are function entries. And this is basically a map between a function name and the start of that function, the address at which that function starts. And the symtab usually has an associated string tab section that contains the actual strings it's using. So you'll usually see these 2 sections if you're talking about a binary that has basic symbols built into it. So let's talk about our first little trick here, and this is super simple. I think anyone could think of this themselves, but one of the most important things that any static analysis tool can do is just determine where do functions start and where do they end. And so in theory, this could be done totally automatically. You could just have your static analysis tool start at the entry point and trace every possible execution path until you've found every procedure. But in reality, that's not actually really possible. You start running into things like the halting problem, fun things like that that keep you from actually analyzing a binary this way. So static analysis tools try to make use of what information is available, and symbols are really one of the biggest ways that they can do this when those symbols are available. And so the trick here is really simple. I promise they get more complicated from here. But if we create just fake symbol entries that say a function starts at a place that a function doesn't really start, the analysis tools just sort of trust us. And this is particularly effective on x86-based processors because those bad addresses can actually be in the middle of instructions, which causes the analysis tool to just start processing at bad data, and things go wrong pretty quickly. So for these other examples, I try to do like screenshots of everything, but this one doesn't really represent itself well through screenshots because you're kind of breaking the entire binary. So just to describe it a little bit, once you start putting these bad function boundaries, you cause the analysis tools to truncate functions early, to start functions where they don't belong, and this very easily breaks the decompiler and the disassembler. And yeah, in particular, if you start inserting function addresses in the middle of instructions, things disassemble correctly and your whole analysis starts to fall apart. This is really simple, so let's try to get into the more complicated stuff. And we're going to talk about what's called no-return analysis. So no-return analysis is a step of the decompiler and, for the most part, regular compilers as well, where the goal is to try to determine whether a function will ever actually return. So something like exit is called a no-return function, and that once you enter that function, control of execution never comes back to where it started because the process just ends at that point. But it doesn't have to be something that terminates the process. Throwing an exception in C++ is also a no-return function because control of execution is going to go somewhere else completely, meaning that it'll never actually return from that function and continue executing. So to use like a really dumb example, I hope I made that big enough. let's say you've got this code here where you call exit, then you have something after it, you're just printing a string. Really, any compiler, if you give it the opportunity to optimize at all, it's going to notice that that string that comes after the call to exit, nothing's ever going to happen with that, because when exit gets called, the process is going to end. And so the compiler will probably just try to optimize that away. But let's assume we beg GCC not to do that, so that we can see what it looks like in the decompiler. The decompiler is going to do that exact same thing. It's going to realize, well, you just called exit. Nothing really comes after that, so this is unreachable code. Like that, this is code that will never be executed. What's interesting, though, is that the three tools we're looking at, IDA, Ghidra, and R2, all maintain lists of functions that they will treat as no return just based on their name. These are the files if you care to look for yourself. But basically what this means is if you name something exit, IDA is going to assume that that function never comes back once you call it. So this is a really easy trick. You don't have to modify the binary or anything. You can just compile this yourself with GCC. And basically what we've done here, we've named the function exit. It's not actually going to exit. That's just a name. And then we call it. And we put some code after it that's just going to print a string afterwards just to prove that, yeah, we actually did execute afterwards. And so when we run that, yeah, it does exactly what you would think. It says called exit, and then it calls that code that came after it, because our exit function doesn't actually do that. But then when you look at that in the decompiler, you see IDA has taken your word for it, that this is really the exit function, and it's optimized that code away at the end. It's a little more interesting if you look at the disassembler, where we can see it did actually disassemble those instructions. It does know that that's code, but it sees it as code that's outside of a function. So that red basically means, yes, this is code, I disassembled it, but it's unreachable code. It's code that's not a part of a procedure like the code above it. And so what we've basically done there is we've created a function that will do something entirely different than what the decompiler says it's going to do by taking advantage of this assumption. And then if you do that exact same thing, you look at it in Ghidra, you'll see about the same result. Ghidra does give you a little warning that say, hey, I'm exiting early because I saw this function call exit. But what's particularly interesting is when you look at the disassembly, it didn't even bother to treat those bytes after. OK, hard to see that. Yeah, sorry. Take my word on it. Those should be instructions. In reality, those are just bytes that were not disassembled. And so we've essentially caused it to not only treat this as not a full function, we've caused those instructions to not even be treated as code, which has effects down the line where it could miss function calls, it could miss references to things. Essentially, it could miss everything else that that function does. And then R2 does not have a decompiler, so we're mostly just looking at its disassembly. But we can see again here that basically it is considered that function to be just the instructions leading up to that call to exit, and everything after it is treated as something else. And another particularly fun thing about this trick is that it has a tendency to propagate. So if you think exit, as we know, is a no return function. But if you have some function that always calls exit, no matter what, then you can pretty well assume that that function itself is also a no return function, because it's also not ever going to come back. And so this assumption tends to propagate. And there's a couple ways we can exploit that. A really dumb way might be to just take something that's called all the time, like malloc, rename it to exit, so that everything that calls it will be assumed to be no return. Or we could do something a little more complicated, like create a stub function, name that exit, and just call it at the top of every other legitimate function. Not really changing the behavior, but making it look like every function starts with a call to exit, which totally breaks analysis. The next trick I want to talk about is name mangling. So name mangling is a concept basically of being able to represent a more complicated function definition just in text format. So there are a couple forms of this you might already be familiar with. In fact, I should say there are a lot of forms of this, like lots of new compiled languages, Go, Swift, stuff like that. They all have their own name mangling formats, but these are the ones you really see because these are the common C++ formats. The first one you might see is the Itanium C++ format, which is used by GCC, all those Linuxy compilers. And then there's the Microsoft version, the MSVC mangling. These are basically two ways of doing pretty much the exact same thing. It's encoding a whole bunch of data, not just a function name, into one complex, weird-looking string. But so basically what these mean is that like a mangled name contains not just a function name, but it could also contain the argument count, the argument types, return values, calling conventions. Especially with the Microsoft version of this, you can encode a ton of different information just into a name. But the one that we particularly care about here is actually argument count. So the reason this is interesting, to get into that, we have to talk about calling conventions a little bit. So again, we're talking mostly about x86, but regardless of what architecture you're using, calling conventions tend to work about the same way, where sure, maybe the first few arguments to a function get passed through registers or something like that, but if you have enough arguments, eventually you're going to start passing stuff on the stack. And so what that means is that the more arguments you have, the more stack space is allocated for arguments. And this puts sort of a requirement on the decompiler of how it has to process that stack space. And so if we can convince the decompiler that the function uses an excessive, impossible amount of stack space for its arguments, it's going to screw up its ability to actually decompile that function, or at least it may, I should say, because this varies a little bit from tool to tool. And then similar to with the no return trick, this also has a tendency to propagate between functions. This is a little more complicated, but so if you were to imagine you've got a function that takes 2 arguments, but you're convincing the decompiler that it takes 100, and some function calls that function, it's only going to initialize 2 of those arguments. You've got 98 of them that are uninitialized. And so it has to sort of make the decision of, well, where did those other 98 arguments come from? And without any information in the function, the only assumption it can really make is that, well, those 98 arguments must have been arguments to my function. And so not only does that first function you've lied about now take 100 arguments, but the one that called it may also take 100 arguments as well, because that's the only way to sort of square that assumption. And so when we talk about this excessive argument count breaking the decompiler, you can then cause a cascading failure where every function that calls that function now breaks, et cetera. And so this is pretty simple when you get into it. Essentially what we're going to do is we're going to create a function with a mangled name that says it has a huge number of arguments, and we're just going to see what the decompiler does. So this is another trick that you don't have to modify the binary for. You can just compile this yourself. You've got this really ugly looking name. It doesn't look any better from my perspective. It's not just because it's small. Anyway, but what this basically translates to is it's a function named A that has no return value and takes a huge amount of integers as its arguments. Every single one of those i's is a separate integer argument. And just like that, you compile this just as it is. You try to decompile it with IDA, and it fails. And the reason for that is just simply that it doesn't have enough stack space to fit the amount of arguments, and so it's not able to make sense of that. Ghidra actually does this a fair amount better. You can see it does actually... can't really see anything there. I'll just narrate this to you. Essentially, what you can see is that Ghidra does trust that we are correct in that set of arguments. That's what all that weird purple stuff is. But it doesn't actually break the decompiler. Ghidra is a fair amount more loose about what you can do with the stack space and still have functional decompilation. So this is ugly, but doesn't quite break the decompiler in this case. And we're not going to look at R2 because R2 doesn't have a decompiler, and this is more of a trick for that. Just quick little aside here, but when I first started messing with this stuff, this worked way better. And when I was preparing for this talk, I realized that this trick had stopped working quite as well in IDA. and I wanted to figure out why that was. So I started looking at it and realized that IDA had gotten a whole lot better at detecting when function arguments are actually used. So if you say something has 100 arguments, it'll trust you at first, but then when it analyzes that function, it'll say, well, wait a minute, you're not actually using any of these, and it'll just optimize those away, and that kind of fixes what we're trying to do. So what I wanted to do, and I was working on this just last night, was figure out a way that you could convince IDA that those arguments are being used without actually like allocating the space for them or anything like that. And I came up with what turned out to be a pretty easy fix, which is just have the stub function you're exploiting call itself. Because at that point, IDA can no longer assume that those arguments aren't being used because they're being passed into a function call. So even though it's a call to itself, IDA isn't able to optimize those away, and our trick keeps working. Anyway, so we've talked about static analysis here. I do want to save some time to talk about dynamic analysis, debugging, and stuff like that. So to do that, we have to talk about dwarf debugging standard. So yeah, the dwarf debugging standard is basically a way of defining debug information in a compiled binary. If you're familiar with it, it's probably because it is the output you get with the G flag in GCC. It's that extra debug data. And so just with the stuff we've talked about so far, we opted to do it all with the symbol table instead of dwarf debugging. But truthfully, you could do all that stuff with dwarf, and it would probably honestly be more of the correct way to do it. The reason we're not doing that is that static analysis tools have a tendency to be less trusting of dwarf data. I think the reason for this, for the most part, is that it can just take way longer. Like IDA and Ghidra will if you load a binary with dwarf data, they'll ask, hey, are you sure you want to parse this? Because if it's a big binary, it could take way longer to analyze all that dwarf data. So all else being equal, if we're able to do something through the sim tab, we're probably better off doing it because that's going to be implicitly trusted instead of requiring the analyst to actually press, yes, parse this for me. But anyway, the reason that we're going to start talking about dwarf data now is because debuggers don't really care. They will just load dwarf information when it's available without asking, or at least all of them that I've tested. And dwarf data gives us a whole lot more flexibility for actually interfering with what debuggers do. So to actually get into the full dwarf standard would take more time than I have here, so we're just going to hit the important stuff here, which are dwarf expressions. So interestingly enough, the dwarf standard defines a Turing-complete instruction set for dynamically calculating values. You could program effectively any logical operation you want in debug data. And so these expressions are most commonly used for dynamically generating addresses in memory, and this is what's called dwarf locations. So dwarf locations are one of the more common entries you'll see in dwarf data, and they are in turn usually used by what are called dwarf variable entries. So if you're talking about like this global variable is located at this address, in dwarf data that is implemented through a dwarf location, which is itself a dwarf expression. And so the reason for this complexity, this Turing-complete programming language, is because dwarf expressions need to be complex enough to handle all sorts of situations, like dynamically sized arrays, something you can't just build into the binary of like a symbol table because it's going to change from run to run. It could also have to do things like dereference pointers dynamically if you're talking about parsing like complicated structures or something through your debugger. And dynamic memory ranges, things where it's not going to be mapped directly at runtime, heap, stack, things like that. So let's talk about how we would go about hindering debugging using dwarf information. So our goal is pretty simple. We want to make it difficult to debug, and we want to do it through a pretty specific process, which is we're going to create a dwarf expression that wastes as much execution time and as much memory as we can possibly make it do. So the real simple, straightforward way that you might attempt to do this is just do like an infinite loop. Unfortunately, most tools, at least the ones that I have tried, are smart enough to know I'm not just going to try to execute a single dwarf expression forever. They set some sort of limit on however many instructions they're willing to execute, and if you run into that, they just stop. So we have to get a little bit more complicated than that. But dwarf is a stack-based language. I'm sorry, stack-based interpreter, I should say, which means that as you're adding stuff to the stack, that stack is growing, you're consuming more memory. So our goal here is we're going to create an expression that uses almost the maximum amount of instructions we can use. I think Ghidra was really the example I was using here, where it'll do 1,000 instructions and then stop. So let's say we use 999 instructions and expend as much stack space in those 999 instructions as we can. And then that will be stored in some way that we've consumed some memory that's going to continue to be used for the life of that debugging session. And so conveniently, Dwarf supports procedures where, just like any other programming language, you define some set of instructions, and then instead of needing to duplicate those, you just make a call and then execute all of that at once. And so this lets us save a lot of space where we're doing this, where we define our evil dwarf expression once, and then we create a whole bunch of dwarf locations that all call that expression so that we don't have to keep redefining it. And so in practice, this actually works really well. Most tested debuggers totally struggle with this. They spend a whole bunch of time loading. Maybe they run out of memory. Maybe they give up at some point. But by the time they've given up, they've wasted a whole bunch of time. And the person sitting in front of the debugger is pretty frustrated with it. If they don't give up, then they're just using so much memory that they continue to be slow enough that it's almost unusable. So this may not be a complete substitute for like a full anti-debugging solution, but it works pretty well, and I don't know if I've seen this done before. Okay, so let's talk a little bit about symbol stripping. So the very obvious flaw with everything we've talked about here is that this all relies on these fake symbols we've put in place being there. All you really have to do is strip the binary and everything goes away and you have no problems anymore. So to deal with that, what if, let's talk about if we could detect binary stripping and react to it dynamically. So what does it actually mean to strip a binary? So I'm using the bin-util strip utility as an example here, but I think this is true of pretty much anything you could be using. Stripping a binary basically works by removing the sim tab and removing all the dwarf sections. So we're not modifying the code, we're not modifying the data, we're just removing a few sections from the binary that aren't really necessary for anything. So this isn't quite as easy as it might sound to detect that this has happened, because these sections aren't mapped into memory anyway. It's not like the data segment where you can just look for it in memory, see if it's changed, anything like that. Like we said, these are unnecessary sections for execution, so they're not going to be in memory either way. So we want to look for something we can key off of in order to determine that our binary has been stripped dynamically. We could do something like read our own file, but that feels a little flaky to me. I'd rather do it in memory based on some other metric. And so there are probably a few ways you could do this, but the way I went about doing this was to use the elf header. So the elf header is basically the first structure of an elf file. It's literally the first few bytes of the file, and it defines a whole bunch of stuff about that binary, including the number of sections that make up that binary. And conveniently, it's mapped in memory at startup. And in fact, it's typically the very first thing that's mapped in memory. So basically, we can detect binary stripping by reading the elf header and just comparing this field, the shnum, the number of sections, to a known good value. So we compile it. We know that when we have our symbols, we have 31 sections. If that number changes, somebody did something with our binary. They must have stripped it. So here's an example of doing this. We've got this. OK, that could be a little bit bigger. I'm sorry. We've got this function get shnum. We're going to call dlopen to dynamically get the address of our base pointer. which is the very first thing in that base pointer is gonna be our elf header, and we're just gonna get the sh num from that, compare it to a known good value of 31, and based on that, we're either gonna take some action, well, based on that, we know whether or not we're stripped. And so in this case, we're just saying, if we're stripped, print we're stripped. Otherwise, we're gonna print we're not stripped. And this works pretty well. I mean, dynamically, it works just fine to detect the fact that you have been stripped. But I think we can take this a step further. I think it would be cool if we could actually make something that decompiles differently based on whether or not it's been stripped. And this is a little bit different because, again, the static analysis tools are not going to run the binary. So we need to take advantage of something within the static analysis, not something that's going to occur at runtime. And so for this, we're going to talk about what's called dead code analysis. This is another thing, another intersection of decompilers and regular compilers, but both of them can basically detect and remove unreachable code. So to take another really dumb example, we've got this function where we've got a variable, we name it a, we assign it the value 1, we add 1 to it, and then we compare it to 2. And based on that comparison, we're going to print some message. And I think anyone could tell you that that first one puts a equals 2 is always going to be executed because there's really no variability here. So again, you give this to GCC or something and you give it any opportunity to optimize this function, it's just going to turn this whole thing into puts a equals 2 because it's going to tell that everything else there is unnecessary. I can just figure that out myself. But if you ask it nicely not to do that, we can, again, see how the decompiler works. So I've got the disassembly on the left, just so you can see that this is, in fact, it's not the compiler optimizing this way, it's the decompiler. So we've got here essentially that same logic. I know you can't really read this, I'm sorry. But we're assigning a value 1, we add 1 to it, we compare it to 2, and based on that, we're going to print that message. So even though this is straightforward and should be optimizable, the compiler has not done that, but we can see that the decompiler has. It's going to take that and say, well, because I know what is always going to happen here, I can I can turn this whole function into puts a equals 2. And so we can take advantage of this dead code elimination to basically trick the decompiler into treating a function differently based on whether or not our binary is stripped. All we really need to do is do just what we were doing, referencing the elf header, but we need to do it in a way that is simple enough that the static analysis tools can resolve it and figure it out themselves. So we're going to do a little bit of a modification to our example from before. In this case, we're using position-independent binary, no ASLR or anything like that. You don't strictly need to do that, but it makes this example a whole lot easier. And so we know our elf header is at a fixed address, that 4000, et cetera. And we're just going to reference it directly by that address, compare that value to 31, and then see what it looks like. And again, this works pretty well. You put this in the decompiler when unstripped, and both IDA and Ghidra have the exact same output. Trust me, I know you can't see the one on the right. They're just going to optimize that whole function to just that message that says not stripped. You strip that binary. That's not much help. I'm just going to skip that. You strip that binary, and you see that it's taken the complete different execution path. It's analyzed that function and said, this is the only thing that can happen. Therefore, I don't need that code there at all. And so this is a very simple example, but we've created a function that will decompile completely differently just based on whether or not the function has been stripped. And you could make this as complex as you want. You could add whatever code you want into those blocks, and the decompiler would act the same way. Let's tie all these tricks together. To put all this together, we're going to create an elf that has a whole bunch of fake function entries. We're going to put them at misaligned addresses as much as possible. We're going to name these fake functions things like exit or throw exception, or use those mangled names that use a whole bunch of extra arguments. We're going to add our debug data, our dwarf entries that waste time and memory when the debugger is attached. Excuse me. And then finally, we're going to add that little bit of code that both detects stripping and modifies decompilation when the binary is actually stripped. And so with all of this, what we end up with is something that significantly hinders static analysis against all of these tools, is much more difficult to debug, really gives the debugger a run for its money, and modifies its behavior in a pretty subtle way when it is stripped so that we can prevent just simply removing all those protections and then debugging it like it's normal. And then all of this is done with really low overhead. Like we said, all of this symbol information isn't actually mapped into memory, so you're not adding anything to like the memory overhead of the process. You are increasing the file size a little bit, but even that, you're talking a couple kilobytes at most. And we're not making any changes to existing code. If we are using that last trick of like detecting a stripped binary dynamically, then we do have to add a little bit of new code, but it's not like an obfuscator where we're recompiling the whole binary with a whole bunch of like packed or obfuscated code or something like that. So I think this is a pretty difficult binary to reverse engineer considering how little overhead we've gone with it. And so the last thing I want to talk about is how this applies to Windows. So we've mainly been talking about ELF files, but most of this does apply to executable files as well. In fact, you can actually just attach a symtab or dwarf entries to a portable executable. That's not typically how people do it, but the analysis tools will actually parse that. In fact, if you use like min.gw as your compiler toolchain, that's actually how it works. It just attaches dwarf debug information to a PE file. Windows also has its own equivalents to most of these standards, which I would imagine work about the same way. I haven't really tested this stuff, but I would imagine that it works about the same, just with different standards. The one thing is you would probably have to find a different trick to detect stripping because that ELF header trick that we were using isn't going to be available anymore. Yeah, so that's it. Thank you very much, everyone. I'm a little early, so if there's any questions, I'm happy to answer. Yeah. No, I haven't. So I actually looked. Oh, yeah, sorry. The question was if I had seen examples of this from major manufacturers. I have not. I was actually looking quite a bit. I figured maybe that the dwarf stuff had been done before, but I cannot find any examples of it, no. Yeah. The question is with function mangling if I had to disable. So let me ask. You're saying from the perspective of like IDA or something, did I have to disable anything in? Oh. Right. So the question is, yeah, when compiling with those mangled names, if I had to disable anything in the compiler. So I guess in a sense I was disabling it in that I was using GCC, not G++. So technically I was just using, those are just text names that were technically valid C names that were that GCC had no problem with. If you were to use the MSVC version of that, because those are not actually valid names, you would probably have to like edit the binary or something like that. Yeah. Yeah, so the question is about existing tools. So I am hoping to release a little bit of this stuff. I was hoping to have it ready today, but real life work got a little busy. Luckily, a few of these tricks you don't really need any special tools for. You can do it with just the compiler, but when it comes to the dwarf stuff, you really do need to start building it yourself. So there's a nice library called libdwarf that I believe believe was maintained by Avast, but is now deprecated. It's a little hard to get working because it is a little old, but it seems to be the only tool out there for building dwarf debug information like from scratch, unless you want to jump into like the GCC source, which I wouldn't recommend. That would be my recommendation there, and hopefully if I have any sort of work ethic over the next couple weeks, I'll be able to release this stuff. Okay. Well, thank you very much, everyone.